Got it. Okay. So let me dig into a little bit about the architecture so that you have a sense of how the architecture works. And then we'll come back to how to program it. So each one of these tiles, there's lots and lots of tiles. We can sort of spread it out, but basically there's different kinds of tiles. So the most important kind of tile is a tile that actually does some processing. So here we have that vector VLIW processor, has its own program counter, has its own program memory, has its own local data. And it also has some data movement that it can do. So when you execute load and store instructions on this processor, it's going to access its local memory, or it can also access some of the memories of the cores around it. So there's sort of this localized shared memory, but it's not global shared memory. Right? You can only access a relatively small amount of data. If you want to access a large amount of data, in fact, in order to access any interesting data, you need to bring it from off-chip. And so the way we bring data from off-chip is from down here at the bottom, we feed data into that streaming interconnect. The streaming interconnect is going to connect to the DMA. DMA is going to write data or read data from the local memory of the chip. So the idea is that the DMA is taking care of the coarse grained data movement, and all that the core has to do is just do the local data processing. And of course, you're going to pipeline everything, so you pipeline the communication with the computation. And if you manage to do that, then you can keep the vector multiply add unit busy almost every clock cycle, and then you probably have a really efficient design. That's kind of the basic gist of how this is going to work. You see there's also a block called locks. So the processor in the DMA can synchronize. They need to synchronize. And so there's actually hardware support for lock operations to keep the DMA and the processor from, to allow them to coordinate on the access of data. Down at the bottom of the chip, kind of in a row, there's what we call mem tiles. So mem tiles are kind of very similar, except they don't have a processor, but they do have a lot more memory. So this is the idea of this is it sort of acts like your L2 cache, allows you to bring data from off chip, store it on chip, maybe have more storage so you can keep data alive on chip without going back and accessing it from external memory again and again. But it kind of has the same sort of DMA and lock scheme as a processor block, although the connectivity is slightly different. So for instance, in the mem tiles, there's no horizontal connectivity in the stream switch. The idea is you're just going to continue to bring the data straight up. And the DMA can also access some of the neighboring memory tiles. So that gives you a little bit more data that you can access from a single DMA point. And lastly, there's also a DMA at the bottom of the chip. So this is what we call the shim layer. And what this allows you to do is to read data from off chip, so like from an external memory bus, and bring data into the streaming interconnect so that you can process it on the rest of the device. Okay. So does anybody have any questions at this point? Yeah, in the back. Yeah. So if you think about a DSP in an FPGA, the DSP blocks are really just a multiplier and an adder. So if you take a sort of a normal pattern in an FPGA would be to take a DSP with some memory to store the data and some FPGA logic to control it, right? So this is basically the same thing. It has the processing, the vector operations in the core. It has a program counter and instruction decode. So you don't need FPGA logic to do that. It has local memory. And so that's your sort of DSP block. The processor is very much a DSP-oriented processor. So it's a exposed pipeline VLIW. It has a vector multiply accumulate instruction. If you're used to programming like signal processing DSP processors, it's going to look a lot like that. Yeah. Mm-hmm. Yes. So all of this is in the chip. It's all hardened in the die. Yeah. Okay. So the question is, we have L1 cache. There's L1 memory. If I go back here, there's L1 memory, and then there's program memory. So this is a Harvard architecture kind of DSP. So we separate the program accesses from the data accesses. Yeah, so this is the instruction memory, but these aren't actually caches. So the key thing, if you look here, all of the memory buses are in red. So a processor can access memories here, but a processor can't directly access the L2 memory, and it can't directly access external memory either. So the only way to bring data into the device isn't through like a cache miss, right? So the core doesn't execute a load and then like have the cache figure out that it needs data from external memory and then go through a sequence of caches to fetch data from external memory, right? So here, in order to get data from external memory, we have to write something into our program for the device that is going to program the DMAs to do memory accesses and stream the data up through the interconnect to a processor. Does that make sense? Right? So there's certain applications that this is not a great choice for, right? If you're working in a database, if you're doing pointer chasing and things like that to very large pieces of memory, very bad architecture, right? If you're doing machine learning, where you're doing large matrix multiplies, then actually a pretty good architecture. Okay. Yeah. Great question. I'll come back to that. So we have been building open source tools. There is a kind of like a product flow that we call Vitis and Vitis AI. So for instance, for machine learning, Vitis AI has basically an overlay. It's a program that runs on the device. And there's a compiler that takes PyTorch code and figures out how to turn it into overlay instructions, right? So it's really a fixed architecture, a fixed program that's running. One of the things that we've been doing in open source is trying to build a flow where we actually generate a very application-specific program. And so the hope is that people then can then, outside of AMD, can build lots of interesting applications. So that's one of the things that we hope to get you excited about doing. Has anybody heard of mlir? Okay, Ryan, you don't count. Good, glad to hear it. So mlir is actually a new modern compiler framework that's very extensible. That's something that we've been using very heavily. All of our compilers are built using mlir. I think if you haven't looked at it and you're at all interested in building tooling, I would highly recommend it. It's an open source project that's all part of LLM now and is very tightly integrated with doing backend code generation. Also has a lot of nice frameworks at the front end for doing machine learning. I think I need to step out. Can I talk to you? Can you take over? Thank you, Crystal.
We're good? Yeah. So he gave me a challenge, right? Because this is the part about mlir, which I'm less familiar with. But what this part of the presentation is trying to show you, I will summarize it in my words, is that our technology, how we open sourced and how we make sure that you can use our architecture, for that we need to make sure you have the proper intermediate representation in the multi-level intermediate representation tool framework like mlir is. And what you will see here in these examples is that every architectural component that Steve described before, we have a counterpart in that in mlir. And so if you would like to, and what the tool actually does for you when you lower through the compiler, is that you can make a very structural description in that intermediate representation so that in the end, you can get to a design that you can run on the AI engine processor. And so in this case, you see that we are pretty specific about the fact which AI engine tile you're really using, which core you're using, which is there on the top. And then because you want to do something with data, and let's make the assumption that the data is already brought into the local memory by properly setting up the data movers, then you can do your operation like you had in mind. In this case, I think it's nothing else than doing a simple addition on top of that. So this is completely different, right? So the overall view of our flow is that indeed you can inject from the high level something from PyTorch. From that, in the higher levels of the tool flow, you start to generate more abstract intermediate representations. With these dialects, we are very focused on representing the AI engine on itself. So you would have to go through the higher levels and then lower it into mlir. And what I'm showing you here on the screen is, you could say it's a handwritten mlir code to be able to explain to you that we have the rich and complete set in mlir to represent all of the properties of the complete AI engine architecture. So as a user, this is the compiler, this is a tool developer view of the world, right? That's why we're showing the screen intermediate representation. As a user, if you're an application engineer or something like that, you typically don't like to see this. But we'll get back to this, because what we did is to be able to address the needs of, like, I call them diehard coders, people who really like to work, like in Counterpart, you could say at the assembly level of something. So we have built Python bindings so that you can kind of describe the most optimal design you think you could come up with because you think the tools didn't make a good decision. Then you can actually write down at a very close to the metal how you think that application should run. So you would run it, you would write that in the Python bindings. It would then generate this intermediate representation that can go to the backend of our tools, and then you can run it on the AI engine array that is inside of this processor. Laptop is what I tried to say. Steve stressed a lot, and there were questions about that as well, that on the AI engine architecture, one of the big advantages is that we have all of those data movers there. It's also your disadvantage, right? If you want to make a really good design, if you want to make a tool that is supporting making very optimal designs, you properly need to move the data through those multiple levels of the memory hierarchy. So you have to set all of that up. So you need to also be able to express in this dialects how you're going to move buffers around, maybe from the level 2 of the memory hierarchy to the level 1, or maybe physically between neighboring cores, or maybe to cores that are further away. In this example, it's two neighboring cores. They communicate through the level 1. Steve told you before that if the neighbors are physical neighbors, if the cores are physical neighbors, they can directly talk to each other. They don't have to go over that axis stream network. You could, and I hope that's the next slide. There we go. You could, so inside of the AI engine array, every core can communicate to the other core. And if they are not neighbors, they will go over this axis stream network. And for that, you need to configure that. And you need to also configure the switch boxes to set up that communication between the cores that are further away. And this slide is showing you exactly that. We can also express that in the mlir representation. Which we called Cardano, which now is called publicly ADF, which is part of the Vitis tool set. Is that what you were hinting at? Okay. Not yet. Let's keep it at that. Yeah, so that came before we in the research lab started to do a lot of research towards how can we, okay, I'll try to phrase that differently. The Vitis tool set is right now pretty monolithic, right? It's still closed. And we from the research labs and also from AMD as a company believe in making sure and making things available through the open source in a more modular fashion, because one of the promises and strengths of doing things in the mlir framework is that depending on where you are in the abstraction level of your design flow, you can tackle the optimization problem at hand where you are in the flow, and you can kind of plug in other mlir modules that have been developed to kind of tackle that step in your design flow and have the proper optimization knowledge in there. So by opening this up, and that's also why we are here today. This is actually an invitation not only to people who, like me, go crazy and want to hand design stuff, that you would be able to plug in either tool components you already built in this mlir flow, and then suddenly you can bring in your optimization phase towards an architecture like the AI Engine array. So, and as a company, of course, we embrace that. So I'll leave it at that as an answer to how Vitis is structured. So let's see if I'll address that in a little bit. So this is just a little bit more information about the fact that you also have to set up your data movers, which is close to your question. And then because we are in an mlir framework, so if you want to, you can go to this almost very low level that I was showing so far. And if you know what you're doing, you could code it up at that level, right? You could set up all of the buffer descriptors of the DMA. You could configure the flows and the switch boxes up till you know that you properly connected your cores together and have implemented the explicit data movement you had in mind. But it's tough, right? You don't want to have to do that all the time. So that's why we believe so much in mlir. You have these multiple levels, and you can kind of, even within your own dialect, you can kind of build a little bit of hierarchical abstractions. So to address your question, given that Steve pointed out the logs before, right? The logs are there in the AI engine so that you can keep this synchronization between multiple cores. So within the mlir dialect, we proposed a little bit of higher abstraction level, and we start to call them no longer object buffers, but order object buffers, where you more express communication, data movement in a producer-consumer fashion like you would do if you think about data flow graphs, and then you can express it at that level. You could say, for instance, on this, like you see here in the code, hey, I want the ordered object buffer between this core and that core. I know it needs to be able to store so many objects. And then within your compute loops, which you see over here, for instance, on the producer side, AI Engine core, or the consumer side AI Engine core, you acquire an object so that you can do something with it. If you're done, you release it to the other side. Under the hood, we have mlir passes that translate this in the lower abstractions we showed before to set up all of the memory allocation, the locks, flows, DMAs, and everything. And then you can extend this story towards, so we have ordered object buffers, not only for communication at the level 1 of the memory hierarchy, we have ordered object buffers that allow you to set it up to level 2 and even to the level 3. So going through those shim DMAs that allow you to communicate with the external memory. So what we're presenting today, which is focused on mlir-aie, is mainly focused to do all of this statically. But we've shown you the full picture before, where above that mlir-aie level, we have an mlir-aie level. That's where we ourselves are doing research to do it in a more dynamic fashion. And again, we're inviting you to dive into that. Okay. This tries to show you that the power of those abstraction levels, right? It's easy to declare an object FIFO if you then see what happens under the hood and how many code has to be generated at a lower level to really set up that communication. That's why you exactly need that abstraction level. Okay, and there was a question before, I don't know from whom anymore, from you. Yeah, where you asked, how is the AI Engine array similar to or different from a GPU? And the answer is, it's really completely in the data movement. On the AI Engine array, you need to be totally explicit. On the GPU side, you rely on the pre-built caching that is in the system. Now, because we can be very explicit, and because this architecture is meant for a set of signal processing applications which have structured patterns, you can actually exploit that to your benefit, right? You can analyze the data movement patterns, and then you can make sure that you set up all of the data movement either to ordered object buffers or at a lower level so that you kind of either properly prefetch or things like that. You don't need to try to read something, then rely on a cache to make sure that your data is there. That's also why we don't need to be so massively multi-threaded like you are on a GPU, because there you try to hide your latencies to your external memories by playing around with those multiple threads. We don't need that. We can specialize, we can focus, because this is a very adaptable architecture still in the end. So you need to, yeah, the question was whether we every time need to prefetch the data. And I would say yes and no. So yes, you always have to explicitly bring in the data, and you do that by programming up those DMAs. But because in signal processing applications, that is kind of a fixed pattern, you only do that kind of once, right? You load that configuration of those DMAs once, and then you start, you could say almost in an infinite loop, start to process your signals. For instance, in image processing, you would set up the demo that was given, which was processing live video. You would set up those, and it was a line-based processing. So you would set up your DMAs for that line-based processing only once. That was at configuration time, and that was when Steve set everything up. And then you just keep on running, right? Because everything has been properly configured to support the data movement that you had in mind. Sure, go ahead. Yeah, right. That's a good question as well. So the question is, thank you for reminding me. If you have, so it was a machine learning oriented question. If your model is too big to kind of fit in a static configuration, you would have to dynamically reload during your model and the execution of the model. That is correct. And that is certainly supported. This is a fully programmable architecture. And although I said that the communication setup at this level, mlir-aie level, is static, if you're done with that phase, you reconfigure. And the architecture is ready to do that. And that's why we are exploring that higher level, that more dynamic level ourselves. And we call it mlir-aie, but maybe you have good ideas about it as well and now know how to do that more efficiently. I'm trying to figure out what this slide is in the meantime, answering the question. But I think we talked about using external memory that you have to set it up explicitly. So I'll skip over this one. Okay, so another important aspect of the communication support between the multiple cores in the AI Engine array is that axis stream network can broadcast. And so you can bring in data from externally, you load it, for instance, in the level 2, and then you duplicate the same data and you bring it into multiple AI Engine cores. This, for instance, is beneficial in machine learning, where you do like a weight split over multiple cores, but you need to bring in all of the similar activations to all the cores. And then this is the same thing, but then over time. And this is the level 2. And another reason why we have that level 2 memory is that, and this is typical in hardware architecture. So the amount of bandwidth through the shim DMA that we support to the external memory is of course lower than the amount of bandwidth we internally support in the axis stream network. And so it is a good idea, you bring data into level 2, and then you kind of have a bandwidth multiplier there, and then you can spread it out either to broadcast or in other communication patterns to multiple AI Engine cores. You can also use those level 2 memories, and you kind of could have seen that in the edge detect example. If you build one of those ordered object buffers, and you have a machine learning, you would call it a skip connection. It was a simple vision processing example, but we bypassed a lot of the processing steps that we kind of mapped spatially. You would need a bigger buffer. That's why we have level 2 memory as well, right? You can temporarily store pieces in that level 2 memory, or you can do it in the ordered way, which we support to that ordered object buffer. Okay, and then this is the part of the story that I already addressed before, where somebody asked the question at which level you can program things. So because there are people out there, we call them ninja performance engineers that think they know much better than the tool, we actually really want to enable people like that as well. And that's also why we're here today. If you think this is really cool that a laptop you can buy in the store has an AI engine array and you can make specific designs for it, and you cannot wait for all of the fancy tools to be there, you have the Python bindings at your side. You can make a design on the whiteboard and then write down its structure and then use our tool flow to really get it running on the hardware. So the EdgeDetect pipeline you saw running before, we actually coded up using these Python bindings. If you're even more interested, go to the repository. There will be a slide at the end. There are some reference designs there, and you can actually see how we put all of that together. I don't know how I'm doing on time. Okay, good. So this is an example of the two sides of the story, right? So let's focus on the right-hand side of the screen. These are these Python bindings. These are these Python bindings that allow you to set up your complete design. For instance, you focus on a single column of the IPU, which would be 4 AI engines, and you express that you would use a certain compute tile, which is expressed as, I'll do it on the screen, as this tile over here. And then you use some of these order object buffers. In the past, we call them object FIFOs. It's still an old slide with the old terminology. So you declare all of that. You declare which pieces, which physical pieces you're going to use. You declare how you're going to communicate between them. And then for the core you're going to use, so the compute node, the compute tile, you set up actually what needs to be happen from how you use kind of the locks, or in this case, that order object buffer. You say, hey, I want access to one object, then I'll do my compute. And if I'm done, I'll release that object. Of course, when I do something on an object, I want to make sure that I can produce the result, which is in a different order object buffer. So you also had to acquire and release those. So that is a little bit how the application, the AIE device application code looks like. The last part here on the code that I didn't discuss is that you also need to set up that communication to the external memory. And that happens through an instruction stream where you configure which part of external memory you're going to put onto that actually stream network and then make available to whatever part in the IPU that you're currently using. The left-hand side is then where you kind of code up in a kernel what is running on the AI engine core itself, on the compute part of that AI engine core. And in this case, it's a simple example. It is a multiplication of a vector with a scalar. And what we did in this example is say that you have a very big vector, a 4K vector. Through those DMAs, we chop up the vector in pieces, in 1K pieces. That's what we offer to the compute core. We do our vectorized calculation, and then we bring the result back out in the end to the external memory. Okay. I find it fun to code up kernels. So the left-hand side of this slide shows you how you can code up a kernel that runs on the AI engine core itself. And if you want to get the best performance out, you can actually dig very deep, and you can almost go very close to the vector intrinsics over there and really explain to the compiler what it has to do to get back-to-back vector executions. To make it easier for less experienced designers to use the AI engine and also the vector computation capabilities, we are working also in the research labs on auto-vectorization, so that the compiler would look at your input problem description, maybe, for instance, in pure C code. It would analyze a little bit like HLS did in the past to then generate an FPGA design. It would look at those nested for loops, and then it would figure out how it can translate it into code which is optimized for that vectorized execution on the VLIW vector processor part of an AI engine core. And that work is also available in the open source. You can actually see our progress over there. Again, I'm not an expert on that. This is really, really Steve's focus, but that's what that is about. Okay, then the fact that we have those Python bindings so that Ninja programmers can use it already resulted in some interesting collaborations with external partners. This is a design done by ETH Zurich using Python bindings for mlir, for the AI engines. This is a weather stencil implementation. Weather stencils are known to be pretty hard if you want to get a high architectural efficiency. The fact that on the AI engine array, you can explicitly express how the data needs to be moved. You can also explicitly express how you want to spatially map your application at hand on an AI engine array, allows to really get a high architectural efficiency. And that was done with our academic partners at ETH Zurich, and we're able to talk about that at one of the supercomputing conferences this year. So this is one invitation. If you have your own pet application domain, you can do things like this and you can get a good efficiency out. You want to take over again, Steve? Because this is a part I don't know that well. Okay, so then we did present to you that mlir-aie, so the dialect focused at the more structural level to allow you to code up something on the AI engine, is just a piece of the bigger tool story. Of course, we want to make sure that either you guys help us out or we are working on that as well, that for the machine learning set of application workloads, you can kind of build a front end for your favorite framework. I'll get to you in a second. And then you can bring it into an intermediate representation that is kind of shared. And then you can lower it down into an optimal implementation.
What are the data types the support multiplayer?
Yeah, that's correct. So the question, thank you. The question is, for this weather stencil design, what data types did you use to implement the weather stencil kernels, correct? Okay. And then you mentioned correctly indeed that the AI engine core, and I don't think we discussed that today already, supports multiple data types. So it supports floating point 32, it supports int32, int16. And then the lower you go in precision, of course, the higher the compute density becomes, the more vector elements you can process in a single clock cycle. I will have to look at Ali as well. I think the weather stencil design was done in int32 data type, but I doubt, because it is a weather simulation application. So it was certainly 32 bits, but I don't recall whether it was int or floating point, one of the two. Not floating? Okay, so int32. The paper is on there. I'm pretty sure that detail is in the paper. Is there another? Okay. All right. So far, we talked about the more static part, and then there were already questions like, hey, how do you express more dynamic programming concepts? And that's why we are working on something we call mlir-aie, and that allows us to propose a spatial computing model. And so what we would do is we would say, hey, suppose that we have two physical pieces of the engine array, let's say two neighboring columns. We would group them together in segments, and then we can distribute work over those segments, and then we can describe how we're going to assign work to those segments and then launch them together into an air launch. And that brings us closer also to your question, where you were saying, hey, if I have a much bigger neural network, I would kind of recognize certain phases in there, and I anticipate when I go to a different phase that I might have to reconfigure a single, and that would be then a segment here. When you go to the next phase, when you launch that, you would have to reconfigure, for instance, maybe the communication within what we then call a segment. So that is how then we can start to think about both the spatial mapping aspects, but then also about the temporal scheduling aspects. And make sure that over time, like the slide is suggesting, we optimally use all of the resources available in the AI Engine array. To show you the flexibility of the mlir framework that we build on, one of the questions before was on Vitis, and I answered, hey, we like mlir so much because it's modular. You can kind of plug in different pieces depending on what you try to achieve, what your application domain is, and also at which level in the design flow you're working. One collaboration we had, and that was with an intern, is that he built the front end to allow to bring in Triton code into our flow and then still lower it down to the AI Engine array. So that is an example of an invitation towards more the tools people in the audience, how they can work with this framework to build extensions or other things. Triton is like, you want to answer it, Steve?
And the basic idea of Triton is that it's kind of designed for GPU programming. But one of the challenges with doing high performance GPU programming is that you start needing to build programs that are kind of aware of memory hierarchy. If you write naive programs, then you get poor GPU utilization. If you want to get very high GPU utilization, then you need to take into account a lot of very device-specific things. So the idea of Triton is that instead of building a smart compiler to do that, you expose more of the memory hierarchy to the programmer by allowing them to write kind of small tiles of processing and then to explicitly say the order in which you're doing it and how things get distributed over the different parts of the GPU. So the idea of this project is basically that's exactly the problem we have. And so maybe we can also take something like Triton and expose it to a programmer so that they can, which would give them a very Pythonic way of, and maybe a very GPU feeling like way of programming the AI engines. Well, so threads are nice because they allow you to express the parallelism of computation, but they don't really allow you to express how the data moves around, right? So that really ends up being the challenge, is getting the data in the right place at the right time. So just saying that the compute is parallel kind of isn't enough. And especially in machine learning where you have relatively large data sets that you need to deal with. The activations are big, but oftentimes the weights are really big. How you bring the data, just bringing the weights in off of chip, from off chip, on chip, and how do you manage, well, I have a batch of data that I'm all processing with the same weights. How do I process the batch in the right way at the right time so that I get the most amount of data locality between the weights that I am, between my inputs, the weights that I'm processing, the activations maybe from the previous layer. You kind of need to balance all of that. And so when that's something that is very similar between AI engines and GPUs. The main difference is that in a GPU, you do have the cache hierarchy to allow you to build it poorly. Whereas in AI engines, we don't, right? So you are forced as either as a tool developer or as a programmer to take into account the fact that you can't access external memory directly, right? You have to build a communication pattern. You have to build a communication architecture that's going to bring the data off chip, on chip, and manage it on chip, and in a very conscious and intentional way. Does that kind of make sense? Sorry, lunch didn't sit well with me. Do you want to keep going, or do you want me to take over? Tag out. Thanks a lot. So this is just kind of an example of a relatively simple piece of Triton, but we get into the lineage dialect, and the lineage dialect is in mlir is basically a way of expressing a lot of very abstract computation in a way that you can manipulate it in the compiler. So from lineage, we can go into air, and then from air, we can lower into the very architecture-specific representation of for AI engines. We've also been building a lot of debugging and tracing kind of infrastructure that's really important, obviously, if you want to build real systems. So we've been starting to build this up in open source. This is kind of an example of the kind of trace that you can get out. And obviously, one of the things that you want to make sure is that you can actually pipeline the communication with the computation, right? So you want something like on the bottom as opposed to on the top. And the device actually has a lot of built-in tracing infrastructure that we can connect to. We can bring all the data out, decode it. And in the end, what you have to do as a tool developer is expose it to somebody who is a programmer in a way that they can make use of that information, right? So obviously, this is the kind of thing you're very familiar with in a CPU world. You're very familiar with it from using GPU tools if you're doing GPU programming. If you're familiar with FPGA tools, you have things like shipscope. This is, obviously we need something very, very similar. Even printf is kind of hard. So if you're used to doing printf debugging, you don't have an operating system on the processors. So you need to get the data out some other way. So here, this is basically an example of code that is C code that would run on a processor. It allows you to essentially write a printf-like call. But then the data gets extracted out and sent to the host processor, where the host processor can decode it and actually give you a string on the console. That's another piece of infrastructure that we've been building up in open source. So that's the talk. Yeah, question. Yeah. So in simulation, there's a different trick that happens. So when you're running in simulation, you can run code on the processor that actually traps into the simulator. So the simulator actually has a printf kind of like instruction that doesn't show up in system, but it only shows up in the console log of the simulator. This is actually something that you can use in system, and so you can cheat, basically. You don't have the backdoor that you have in simulation. So definitely we invite you all to take a look at the open source repositories. There's mlir-aie and AIR. We also recently, I don't know if Christoph talked about this, AMD recently acquired a company called nod.ai, which is one of the big contributors to IRI. So IRI is sort of becoming the Clang of machine learning in the mlir world. So I think what we're working on right now pretty heavily is taking all of this infrastructure and integrating it into IRI so that people can have an end-to-end machine learning tool flow. So with that, I'll take questions. I think in the front first, and I'll get to you in the back. Yeah. Yeah, well, I mean, ultimately, flops is really important, right? Oh, sorry. The question is, how do we measure performance? And the answer is yes. Measuring performance is kind of important at a certain level. If you have a machine learning network, you care about how fast you can run it. What we really usually focus on a little bit more is actually not the absolute flops, but more the efficiency. So if I can take a big network and I can implement it efficiently, that's good. If I can take a small network and implement it efficiently, that's good. A lot of like big GPU training systems, they scale up and you get scaling by adding more and more GPUs, but you don't necessarily gain efficiency when you do that. And so, here the goal is really to implement what you can implement as efficiently as possible. And so usually when we think about it, on a small device, we think about, how do we get in the, let's say 80% efficiency. If we get there, we feel like we're doing pretty good. If you're only getting like 20% efficiency, then that's pretty lousy. Mm-hmm. In terms of absolute performance? Yeah. So the absolute performance of like what's inside the laptop is small, right? You get much more performance out of the GPU, even in a laptop. The big difference is efficiency. right? So for a laptop environment, that matters a lot because battery life is really important. So you want to be able to log into Zoom and you want to be able to do your Zoom machine learning processing, or I should say Microsoft Teams. You want to log into Microsoft Teams and do your processing in Teams, but not impact your battery life very much. So if you end up to the point where I have to, every time I log into Teams, my GPU turns on, the fans spin up, and I get this very loud experience. That's not what people are looking for. Right? It depends a lot on the GPU. If you want to. Yeah. So I think that the end result is one of the sayings that I come back to a lot is that if all you care about is performance, then you should go buy a supercomputer. And if you say, well, that's dumb, the answer is you care about something other than performance. Maybe not explicitly, but implicitly you care about cost or size or portability or power, or you care about something else. So definitely, we have high-end GPUs, and this is not intended to be competitive with high-end GPUs. It's not intended to be a training device, for instance. It's not intended to scale up to very, very large data centers full of processing, right?
And that's why Steve has That's why we had the first slide at the beginning, right? We first motivated that if you want to build and be able to build continuously more compute intensive and energy efficient architectures, you have to go heterogeneous. So that's why we have AI engines, and they're good at their type of application processing. And GPUs are GPUs, right? And they're meant to do the task that they were built for.
I would also add, even in the GPU world, we build different kinds of GPUs for different purposes. So if you want to buy a gaming GPU, it's actually pretty different from a high-end data center compute class GPU, because there are things that you need for gaming that you don't need if you're doing compute. And so when we build a compute GPU, we rip all of those out. And when you're building a compute class GPU, you care about things like high precision floating point and things like that you don't really need in a consumer gaming kind of GPU. I'll come back to you. I think there was a question in the back. Okay. Yeah.
Is there a point where the GPU is like, hey, it's just like, it's like a workhorse PU,
yeah,
not a GPU?
Well, I think definitely if you look at like the NVIDIA Hopper and the AMD MI250, MI300 GPUs, they're not gaming GPUs, right? So for instance, like you can't get if you took one of the big AMD GPUs for computing and you put it in your Windows machine, we don't even have drivers that would make it show up in a game. It just doesn't. We don't build that software. I think that's a place where NVIDIA actually builds a little bit more heterogeneous environment where there's more crossover, at least at the software level, between the compute GPUs and the graphics GPUs. And in the AMD world, there's historically been a little bit more of a divergence there. In the back. Yeah, so we also have boards with them. The difference is that the boards that we typically look at are kind of data center class boards. So they're relatively large devices. They're relatively expensive. You need a server to put them in. The server is loud. And so, there's sort of a lot of infrastructure. So at least certainly to get people started, we think the laptop route is nice. Or there's even these little NUC boxes that are, kind of like I think of it in terms of Mac Mini form factor because I'm that old. But they're like 6 inches on a side or something and 2 inches tall, and it's all you just have. There's no screen or anything. It's just a place to plug your USB keyboard in and your monitor if you want to monitor, and that's it. Yeah, the question is, who is the hardware targeted at? So one thing you see, I think, across the board in AMD is that we have parts of the company that build fundamental technologies like CPU cores and GPU cores and FPGA and AI engine and interconnect and memory controllers. And then there's other parts of the company that put those together to build devices that are sort of market specific or for a particular market. So, the GPU technology gets rolled into big MI300 kind of compute GPUs, and it gets rolled into GPUs that are better for gaming. AI engines are something that actually fits in a number of different markets, right? So the laptop here is something where the reason for it being is to support a few features of Teams, right? That's why that's why it's there, right? But our hope is that people can build new applications with it. We also put it inside FPGA designs where people can build kind of a much broader class of applications. So for instance, a lot of automotive machine learning kinds of applications are things where you want to run very low power inference, and you want to have all the other stuff around it that kind of looks like an FPGA and allows you to build designs with very flexible interfaces, right? So there's kind of a market-specific role for the laptops and the SoCs, and there's a market-specific role for the big FPGA devices, and there's other markets for the smaller FPGA-like devices. Yeah. Yeah, so I think cryptography is a really interesting one. I think one of the thing to have in your mind is that the processors here do multiply accumulates really well. Vector, multiply, accumulate. If you're doing things that don't really vectorize well or don't resort down to multiply accumulates, then they're probably not going to be terribly efficient. In fact, they might not even be more efficient than just doing it in an FPGA. So I think if you have cryptography applications where you like, okay, I see how this is going to vectorize, it's going to be very multiply accumulate heavy, then that would be great. If you're looking at things that aren't very multiply accumulate heavy, maybe applications that hit maybe weird floating point operators, those are things that we can build in FPGA fabric, might even be more efficient than doing it in AI engine. Question. Yeah, so the question is, maybe we should build a pink board with AI engines. Great idea. How cheap does it need to be?
So generally, the laptops or desktop computers are, I think there is share with each other, right? Like I said, something like people who in the application build, yeah. So even like the graphics drivers are like supposed to be working with multiple computers. So if there is a AI engine in AMD laptops only, so how would like somebody write the application for that? Or is there like some sort of like something like
yeah, so the question I think is if AI engines are only present in a few kinds of laptop SoCs, then are people going to ever target them? The answer is, well, maybe not, right? But I think we need to get people to start using them, and I think what we have, like the little NUC boxes, are actually a really great way to get started, and they're really cheap and they'll run Linux and I think really fill the niche of what Pink was trying to do for AI engines. I think there is a question of how do you take new technologies and that are that are different and trying to be differentiating and innovative and get them over the hurdle of, well, making them not so unique and exotic anymore. And that's definitely, I think, coming back to open source, this is really part of what we're trying to get in open source, is to get people able to use them, to put the tools out there so that maybe we can have a wider variety of people building applications, a wider variety of people building tools, because maybe we didn't get it right? Maybe somebody out there, like really smart students, has an idea, and they got, and you're going to figure it out before we do, right? That's very possible. Yeah. So the question is, are the AI engines themselves different between different targets? And the answer is no. Within the version 2 version 2 architecture, all of the AI engine cores are the same. So the place where things differ a little bit is when it starts to come down to the system integration. So that shim layer that I talked about, in the FPGA devices, you don't necessarily have a DMA in every column. In the laptop device, there's 5 columns and 4 of them have a DMA at the bottom to communicate with memory. So you actually have a little bit more flexible memory access in those devices than you do in the FPGA devices. I suspect that that's probably the end of time. Oh, my battery is low. Okay.
But I think they're going to be around.
Yeah, happy to answer questions offline.
Yeah, please stop them and ask them more questions. Obviously they're interested in working with you all, so please talk to them and work with them. This is a super cool technology. Thank you both. Amazing technique.